today class we're going to be talking about types of reactions. So pull out a piece of paper. Types of reactions. So when we're exploring recipes in chemistry, when we're exploring reactants and products and the reaction therein, often they will fall into several categories of reaction. In fact, in this course, if I ever ask you to do something called predicting products, it will be for sure one of these 5 types of reactions we are going to explore today. So let's just make a quick note of that. Most reactions we explore can be categorized into one of 5 different reactions. And I'm going to shorthand reactions today like this. Now, the first type of reaction we are going to explore today is a synthesis reaction. A synthesis reaction. Now, I'm going to be using what's called the general form for many of these reactions today. And I'm going to explain what these letters mean, but just don't be super confused by this right now. A plus B gives you C. So that's going to be the general form of a synthesis reaction. Here, A and B can represent, so A and B can represent either an element or compound. And what do you think C represents? Well, it's a product, yes. It's going to be just a compound, though. Obviously, if you have multiple things becoming one thing, C will be a compound.
Mr. Saul, should be C or should it be AB?
C is fine. It's forming something new. AB can represent either an element or compound, and C will be a compound. I don't know, my markers are running out here. Will be a compound. Okay, so I'm going to demonstrate for you right now a synthesis reaction. We're going to be making some water. Now, we're going to be reacting. What are the components of water? What are the 2 elements you find? Hydrogen and oxygen. So we're going to be reacting hydrogen. Actually, let's test you guys a little bit here. And oxygen, and we're going to be forming H2O. Is that the correct formula for the production of water? What do you think? Is that the correct formula for the production of water?
No.
Why not?
It is not balanced.
It's not that it's not balanced. You're right, it isn't balanced. But I forgot something else.
The atoms, we didn't put the 2.
There we go. Right, so this should be H2 and O2, right, because they're the Hofbrinkel elements. And now if we were to balance this one out, how would we do it?
You would need 2 hydrogens and 1 oxygen.
That wouldn't balance it. You're right though, we need to put a 2 here. That's part of it.
Okay.
But that's not balanced. What do we need to do now?
So low.
See it. The block, no, it can't see it. Water jug.
Oh, the jug's blocking you. Sorry. You put a 2 there. So it's important you guys practice, practice, practice. That's how you get good at balancing chemical equations. Alright, let's make some water. Alright, so in this balloon I have hydrogen gas, and what's in the air around us? Oxygen. So we're going to make some water here. If any balloon shrapnel landed near you, please don't pick it up. I'll talk about how I made this in a second.
Was that wishbone?
No, that was a hydrogen balloon.
Oh my gosh.
You can feel it in your chest.
Yeah.
Right? Yeah, it's crazy.
Cool. Did you just gather it in a balloon and then light the balloon on fire?
Yeah, I have the experiment right here.
Oh my
Just
gosh.
missed it.
Oh, he just missed it.
Okay. So we made some water. Now, like I said, don't pick up, if you see any balloon around you, don't pick it up, please and thank you. There's probably some hydrochloric acid residue on said balloon. But that is a synthesis reaction. If you have two things that become one thing, you know it is a synthesis reaction. Okay? That's the key. Two things become one thing. So now let's talk about the next type of reaction. I don't have a demonstration for this one, but you will be doing one with your types of reactions lab. So this type of reaction is the opposite of a synthesis. This is a decomposition reaction. And with a decomposition reaction, it takes the general form of C produces A plus B. You'll notice it looks like the complete opposite of a synthesis reaction. Now C here obviously represents a compound. So C here will be a compound, whereas A and B can be either an element or a compound. Now, if I ever give you a decomposition reaction, when we're predicting products, for example, A and B are always going to be elements. But sometimes I'm going to give you one where you have a very large compound and it breaks into two smaller compounds. You need to realize if you have one thing and it breaks into many things, that is a decomposition reaction. So let's use my namesake here as an example. Let's use some salt. Now, with salt, under very specific conditions, keep in mind this is a very stable compound, right? Table salt, you don't see it randomly turning into sodium, metal, and chlorine gas and killing people. It has to be under extreme conditions, very high heat, among other things, usually the catalyst, to separate the sodium and the chlorine. But if we did decompose salt, what would be your products? Splitting it apart, what would it be? Sodium and chlorine. Would that be right? Would that be right?
Sorry.
No, that's okay.
Oh, here's the bonds.
Oh, thank you. Would that be right? No, it's not right. Why not?
Chlorine needs a 2.
Chlorine needs a 2, right? This is one of your Hofbrinkel elements. I'm going to beat you over the head with that. Right? That's one of your Hofbrinkel elements. So how do I balance this? We have, what's unbalanced first of all? Yeah, so we have 2 here, and we only have 1 here, so we need 2 on each side. How do we do that? Put a 2 in front of here. And now we recount, and we have balanced chlorines, but our sodiums are now not balanced. How do I balance out my sodiums? Put a 2 in front of sodium. Alright, so a decomposition reaction, you have one thing becoming many things. Now you've seen this before in your lives. 100% you've seen examples of decomposition reactions. For example, I've already used this one, but if you've put hydrogen peroxide on a cut ever when you were a kid. Hydrogen peroxide, by the way, what kind of bottles do they store hydrogen peroxide in? Yeah, what color is the plastic? Have you ever seen it?
Brown.
It's brown. It doesn't allow light through. Hydrogen peroxide is quite unstable. It will readily decompose, and when it decomposes, it actually decomposes into water and oxygen. So when you see all of that bubbling, what do you think you're seeing?
Decomposing.
Well, you are, but what are you seeing? What are those bubbles?
Oxygen.
Yeah, it's oxygen gas, right? That's oxygen gas. So this is another example of a decomposition reaction. How would I balance this one out? Do you remember my trick? If it's odd, make it even. That's how I'd probably start this one. We have an odd number of oxygens on this side. How would I make that an even number? Two in front of the H2O. Now we have 4 oxygens and 4 hydrogens, so how do I balance it out? Put a 2 in front of my hydrogen peroxide. Alright, so that's a decomposition reaction. Third type of reaction. Now this is the type of reaction that I actually utilized in order to make that balloon. And this is going to be a single displacement reaction. You may also see them called single replacement reactions. Either one is correct, so single displacement or single replacement. I'll get into these ones next class in a little bit more detail, but generally they take the form of this. So AB plus C gives you AC plus B. Now here, what do you think AB represents? When I give you single displacement reactions, AB here will always represent, I should say AB and AC. These will always be ionic compounds. So for this course, when you're given single displacement reactions, AB and AC will always be ionic compounds. So what do you think the C here represents? Or the B here? Those represent either elements or perhaps polyatomics that they can be turned into ions, right? So C and B, for our purposes, is going to be effectively elements that obviously can form ions. So we'll say C and B here, we'll just say are elements. And again, we're going to get into a little bit more detail tomorrow, talking about, well, why is it that C switched with B? Why didn't C switch with A? Right, it's a good question. So how did I make this balloon? Well, this balloon here, it was zinc metal plus hydrochloric acid. And what did I say one of the products was? I didn't say water. I said we made water when I blew that thing up. But this right here, this is how I made the balloon. I mixed in this flask, in this Erlenmeyer flask here, hydrochloric acid and zinc metal. So this is what I put in here, and what was in this balloon? What was in that balloon? It was hydrogen gas, right? So H2. What do you think the other product was? I'm going to give you a little hint here. Again, we're going to talk about this more tomorrow, but I won't even write it down. You'll switch like ions, right? Would two positive things ever make a compound? No, what do two positive charges do? They repel. What would two negative charges do? Repel. So you need a positive and a negative. So the hydrogen and the zinc here switch spots. So we have now zinc chloride. Right, zinc chloride. Alright, so how would I balance this out? This one's pretty easy to balance. Requires one coefficient.
2 in front of the hydrogen chloride.
Excellent. 2 in front of the hydrogen chloride, hydrochloric acid. Now, on the flip side, maybe you're not switching out the positive ion. Maybe you'll have one that looks something like this. I don't think this will actually form a compound, but that's fine. Let's say you had, I don't know, something like Na2O plus F2. Here, what type of ion does fluorine make? Fluoride ion. What charge will it have?
Negative.
Negative. So it'll actually switch spots with the oxygen here. So here we're not switching the positives, we're switching the negatives. So you'll get NaF plus O2. Now to balance this one out, just for the interest of time, I'm quickly going to do that. So that is single displacement. Next up is double displacement or replacement. Now this one, you are going to be doing a do-si-do. You are going to be exchanging partners. Right, no one's left lonely. Here, C was sneaky, stole A from B. Here, they are switching partners. Okay, so we'll have A, D, and C, B, for example. And in this example, for this class, all of these are ionic compounds. So all are ionic compounds. So we are going to be switching ions amongst two compounds. Now, you've actually already seen a reaction like this. In your labs that you did for conservation of mass part 3, what did you react together? Do you remember? I know it was like 3 days ago. Well, more than 3 days ago.
Potassium iodide.
Yep.
Lead nitrate.
Potassium iodide and lead 2 nitrate. Now, just like the previous example, two positives won't make a bond together, two negatives won't be make a bond together. So they will exchange like ions. So in this case, we can switch around our negatives or our positives, giving us, what were the products you guys found?
Lead iodide and
Lead iodide and
potassium nitrate.
potassium nitrate. Which is fairly easy for the most part to balance. How do you balance this one out? Yep.
You put a 2 in front of both potassium ones.
Yes. Put a 2 here, and you put a 2 here to balance it out. Now, sometimes it may be a little harder to balance. Traditionally, the hardest problems to balance on your unit test will probably be double displacement reactions. I could give you a really, really mean one. Something like, let's say, this one actually isn't super mean, but it's not too easy. Something like this. Now, what was the trick when dealing with polyatomic ions again? Do you remember? What's the trick when you have a polyatomic ion?
Keep it together.
If it remains unchanged, right, if it remains unchanged from your reactants to your products, which phosphate and sulfate are unchanged here, you can treat them as a single unit. So for example, here we have 2 phosphates. How many phosphates do I have on this side? 1. So if I wanted to balance my phosphates out, I could put a 2 there. Now I have 6 sodiums. How would I get 6 sodiums on this side? I could put a 3 here. Now I have 3 sulfates. How do I get 3 sulfates on this side? I could put a 3 here. Is everything balanced? How could I double check to make sure I did it right? You could count the atoms again. It is balanced. So again, once you have enough practicing with balancing, that stuff will just become second nature. Let's look at the, oh, I forgot to write in the word double right here. This is a double displacement reaction. Double displacement reaction. The last type of reaction we're going to be exploring is a combustion reaction. Now, combustion reaction, the formula is going to be way easier to remember, the general form of a combustion reaction. It is always going to be a hydrocarbon, and when we burn something, what do we need to make it burn? Oxygen. And what do we produce? What do we breathe out? Carbon dioxide, and we're also going to produce water. So when we're talking about a hydrocarbon combustion reaction, those are always your reactants and those are always your products. What is a hydrocarbon? What do you think that is? What is a hydrocarbon? What do you think? It's in the name. Hydrocarbon. Yeah, it's going to be hydrogen and carbon. So it's a hydrogen and carbon containing compound. So that is a hydrocarbon. Now, speaking of hydrocarbons, I have here Culligan water jug. And in this little tiny flask, I have methanol. Now, methanol is extremely flammable, and it's actually very toxic. Anyone know what would happen if you drank it? By the way, we use this in like brake line antifreeze. So methanol has a chemical formula that looks like that. Anyone know what would happen if I drank this?
Let's see.
What's that? Let's see. No, I'm not going to do that. It's very toxic. So in small amounts, this will actually make you go blind. Larger amounts, you'll die. However, we do drink a member of the alcohol family. We've been doing it for thousands of years. This is ethanol. Now, ethanol is what you find in beer, you find in wine, you find in spirits. That's what gets you drunk. Does anybody know, can you die from ethanol poisoning? If you drink too much vodka, could you die from doing that? What do you think? No one knows. Really? No one knows? Okay, fair enough. Yes, the answer is yes. Now, it's a depressant, ethanol, and as a depressant, it can actually stop signals going from your brain to other parts of your body. If you drink enough alcohol in one sitting, it can actually stop signals going from your medulla, which is a part of your brain that controls breathing. It can stop signals going from your medulla to your intercostal muscles and your diaphragm. So you can actually stop breathing and die. So super important. If you ever see anyone passed out at a party, it's important they get to the hospital if they are non-responsive. You can save their life if they are on a ventilator, but if they stop breathing, they're going to die pretty quick. You've got about 10 minutes before you suffer from brain damage without oxygen. Now, I am spreading this methanol around in this jug. It's almost all evaporated. Why am I spreading it around? Let me ask this a different way. If I spilt a glass of water on the sidewalk in the summer versus having a glass of water just sitting on the sidewalk, not spilt, which one's going to evaporate faster? The one I spilt on the ground. Why the one I spilt? I kind of heard it mumbled a little bit. Surface area. If you increase surface area, you increase the rate of evaporation. That's effectively what I'm doing here. I'm dramatically increasing the surface area such that it evaporates faster. I'm really just killing time and explaining this to you because I need this to evaporate. But if the gas-to-air mixture in here is really good, it's a very energetic reaction because both of these are quite flammable. In fact, this reaction scares me. So I'm going to have you all go to the back of the room right now. So put on your masks and go to the back of the room, please. Okay. I don't think there's much excess in here. Oh, not even a drop. This one should be pretty good. Okay, let's hit the lights and let's do this. Notice how it's oscillating back and forth? Did you see that? Why did it do that? You go back to your desk, by the way. Why did it do that? Why did it oscillate back and forth? Oh, and by the way, you saw me dump all of that liquid out, all the extra liquid. There's nothing left. Now if you look in this jug, what do you see on the sides of it? Is there now a bunch of liquid?
Yeah.
Yeah, there's a bunch of liquid now on the sides of this jug. Right, it's really hot as well, which is why I can't do that again. Students are like, oh, do it again. I'm like, I can't. It'll melt the jug and it could explode. Now, there's a bunch of liquid on the sides of this container. What is that liquid? What is it?
Water.
Yeah, it's water, excellent. Because what did we produce? We produce a bunch of water. Now, why do you think you saw the big flame shoot out and then it got sucked back into the jug, and then flames shot out again and it got sucked back in? Why did it do that? What do you think it ran out of? Ah, excellent. It ran out of oxygen, right? That's why you saw it sucking that flame back in. So the methanol, as it was combusting, it ran out of oxygen, so it sucked more in, and then it allowed it to combust, and it shot out again. So that's why you had that oscillation that took place. And that's a fun one. That one scares me, though. That one scares me. All right, so let's balance now the reaction we did. So we combusted methanol with oxygen to produce carbon dioxide and water. To produce carbon dioxide and water. So, how do I balance this one out? This is actually kind of a mean one to balance, to be honest. Because oxygen's repeated many times on both your reactants and your products. I would say you should follow my tip I gave. If it's odd, make it even. So let's start by making our oxygens even on our reactant side. How would I do that? How do I make my oxygens even on this side? I can put a 2 right here. Now that I've put a 2 there, let's balance, say, I don't know, our hydrogens next. How many hydrogens do I have on this side? Nope.
4.
Nope. I have 1, 2, 3, 4 times 2, 8. So how do I get 8 on this side? Can put 4. Oh, by the way, what should I balance last? Why oxygens? Because this is by itself, right? All right, how do I balance my carbons out? On my carbon dioxide, excellent. And now lastly, how do I balance out my oxygens?
2.
Put a 2 right here. That's not going to balance it, actually. How many oxygens, or will it balance it, sorry. How many oxygens do I have on this side? I have
6.
1, 2, 3, 4, 5, 6, 7, 8. How many do I currently have on this side? 1, 2, 3, 4. So what am I going to put here? It's not a 2,
3.
a 3. If I put a 3 here, now I have 6 plus 2 is 8. How can I double check to make sure I've done it right? What can I always do? Recount, right? So really you shouldn't be asking me for any balancing problem, hey Mr. Salt, did I balance this correctly? You can always double check yourself. It's a good habit to get into as well. Now, what's in this lighter? Do another example. What's in this lighter here? We've already talked about this, but that's okay.
Butane.
Yeah, butane. It's tetracarbon decahydride. Now, when I combust that, is that a hydrocarbon, by the way?
Yes.
It is, right? It's literally carbon and hydrogen. The reactants are going to be oxygen, right? It's going to need oxygen to burn. And you're going to produce, again, carbon dioxide and water. Hydrocarbon combustion reactions are really easy to predict the products. Because what are your products always? Carbon dioxide and water, right? Now I'm lying to you a little bit here. What do you have in your basement? It's a detector. CO, carbon monoxide. Really, this is only true if you have perfect, complete combustion, right? If you are perfectly combusting all of this butane with enough oxygen, if we start to deprive oxygen from the reaction ever so slightly, you'll get carbon monoxide formed. In fact, you almost always get a little bit of carbon monoxide formed. So I'm lying to you a little bit. You always have a little bit of incomplete combustion. But for our purposes, we're assuming everything is completely combusting perfectly. So we're always going to have carbon dioxide and water. How do I balance this one? How do I balance it? Again, what am I going to balance last? The oxygen. I'm going to balance that one last. Why am I going to balance it last again? Because it's by itself, right? You can add any number there to balance it in the end. So let's balance our carbons first. How do I do that? Excellent. Add a 4 to the CO2. How do I balance out my hydrogens next? Add a 5, do the H2O. Now, how many oxygens do I have on this side? 9. Not 9. 13. We have 8 plus 5 more is 13. How do I get 13 on this side? Ooh, well done. You go 6.5. But can we have half of a molecule? No, you can't, right? So what do I need to do? Multiply everything by 2. So we get 2 molecules of butane react with 13 molecules of oxygen to produce 8 molecules of carbon dioxide and 10 molecules of water. Alright, so those are the 5 types of reactions. Synthesis, decomposition, single replacement, double replacement, and hydrocarbon combustion.